Okay, thank you. So I'm a big believer in conclusions first, based on the advice I got from a chair in my department many years ago, saying that you lose them after the first slide anyway, so say the most important stuff right up front. So what am I going to talk about today? There's two main components. The first component is I'm going to introduce a scalable streaming scheduler for a streaming runtime, and I'm going to show that it scales to having thousands of operators, and it can scale to hundreds of threads. We achieve this by minimizing locks, synchronization, and even global data access. The second component is an elastic thread adapter, which, given that we have this scalable scheduler, can we automatically find the good enough number of threads to actually achieve decent performance on this without any program intervention? And we do this by establishing evidence of performance improvement through trust or not trusting our data and exploring that search space. And we seek the highest level, the highest thread level that we actually have performance, we have evidence of performance improvement that we actually trust. And something that's important is that this is actually working inside of IBM Streams, which is an existing product. And we had to adhere to the existing API that was already existing in the product, because we have customers running the applications in our language, and we couldn't just willy-nilly change the interface. So this all had to be constrained to the existing API that already existed in the platform. So we couldn't just say, well, this would be a lot easier if we could go and change this little thing to make this work. And then off to the right, we have wonderful results. And I'll get to a little bit more later, actually reading through the graph. But the main idea from the results is we have performance results on both Intel system with 176 cores and a Power 8 system with 184 cores. And hey, we scale. And our elasticity algorithms basically find a pretty good performance level automatically. Okay, so to actually get into what we did and give a little more background, so we're working with a streaming language. And this is a asynchronous data flow language that we call SPL, for stream processing language. The three main abstractions in this language are tuples, streams, and operators. So I'm going to walk through the code a little bit here just to give you, so you have a feel for the language and a feel for the programming model. So the first, let me see that, yeah. So this first operator here, it's reading something from an external system. In this case, it's a file. It's the file system. In other cases, it might be the network, or it could be, say, a distributed file system. And this is very common. The first thing you're going to see in some of the streaming applications is ingesting data from the outside world into our streaming system. And then very common, what you will also see after you ingest your initial raw data is we're going to do some parsing on it. We need to turn it from the raw data format that existed in the outside world into some structured format that we're actually going to deal with inside. And then you'll often see some form of, we get the pointer back, there we go. We'll see some sort of, say, filtering on the data, some processing of the data. So once we actually get into the system, then we're going to do things with it. And they say here we're doing a little bit more parsing of it, a little bit more processing. So on the right of the slide, what I show is kind of a visualization of what the programmer tends to think about. And the important thing is that in this language, the only way that these operators communicate with each other is over the streams. So there's no shared memory, which of course makes it great if you're going to do tricks related to automatic parallelism. And what's important to note also is because we're an asynchronous data flow language, we have parallelism all over the place. So we got pipeline parallelism for free, we get task parallelism for free. And if we look at, there we go. We look at this guy and then this guy here, these are annotations where the programmer has said, I know that I can exploit data parallelism here. So give me, say, a data parallelism with 3 or data parallelism with 2, and that's represented on the right side of the graph. So this is not a presentation on the language. I love talking about the language. If you'd like to read more about it, we have a Tuples paper published this year. If you'd like to talk to me about it offline, I'm happy to talk about it. And then also one of the original designers is off in a parallel session at Debs giving a talk. So what we're really going to be talking about is the runtime, the new runtime we implemented for this language in the latest version of Streams. So why did we need to implement this new runtime? So the problem is, our users don't have applications that look like this. This is a toy. Our users don't even have applications that look like this. It's just I didn't have the patience to put thousands of these little circles And also, I don't know if PowerPoint would have been able to render all the thousands of little circles very well. But expand this to thousands, and imagine we have thousands of these little circles. They're all connected by arrows, and that's their application, which is exactly what we wanted them to do. That was the intention. However, we're going to do, and I'll get to why we do this way in a moment. In the latest version, we do automatically for them. We take a look at their thousands of little circles, we call operators, and then we look at the cluster that we're going to actually distribute this to, and we figure out automatically how we're going to fuse these little circles into what we call processing elements, which you can just think of as a Linux process. So every one of the gray boxes here is a Linux process, and it has potentially hundreds of thousands of little circles it needs to execute. We do this automatically now, and we did not used to do this automatically. Our original users were experts. And we have controls in the language so that experts can go in and say, I want these two little circles to execute together, and I want these two little circles to execute together. And by the way, I know where to put my threads. And that works very, very well for experts. However, it turns out not everyone is an expert. And in fact, to the point that we had, so back up for a moment, when we have our applications distributed on these systems, it's not just the application logic that's executing. There's also the platform that actually deals with the fact that it's a distributed system. So we had a customer who called us and said, hey, it's very unresponsive. We submit it, it seems to be producing results, but when we try to interact with it at all, it takes us minutes to get a response from the system. So okay, we log in, we take a look at what's going on, and I realized that they have a 5,000 operator application, which is, because they've done no optimization whatsoever, becomes 5,000 Linux processes on a system that has about 160 cores for about 5 hosts, 160 cores. And of course, all the platform processes are also running on that. So everyone is talking to everyone, and it is a complete mess. And that's when we decided, okay, we need to do something automatic. Even if it's not the best thing, it needs to be reasonable. So because of that, we decided we need to have more reasonable defaults. So we're doing this fusion thing, but this introduces a problem, which is if I now have a processing element on a host, and it's maybe a beefy host, and it has a whole bunch of these little circles in it, I want to be able to figure out where the threads go without the programming telling me where the threads should be. Okay. So given that that's the problem, that's where we're working, what are the requirements that we have to meet? So the first requirement is, if we're going to be able to make this automatically adapt to users' needs, we need to be able to add or remove threads dynamically. And this is important because in previous attempts that we have made actually to solve this problem, this was not possible. We had previous attempts where the threads would just follow the stream graph itself, and they were fixed and they couldn't change. So we need something where we can, independent of the stream graph, control where the threads are. The second thing, and a little bit more subtle, is I want to be able to maintain tuple order. And what I mean by tuple order is that if I have an operator and it emits tuples ABC, and another operator subscribes to that stream, it should receive the tuples in the same order ABC. Now, if you naively do this, this would end up having global state. So we need to avoid that because we're not going to scale with anything that involves any kind of global state. We need to scale. That is, of course, one of the purposes of this. And in order to scale, you're not going to have global locks, you're going to minimize your global access, and you're going to even want to minimize your synchronization. And then the final requirement is, this is a relatively mature product. We have customers that have applications that are running. When they get a new version, things should supposed to just work. So we can't change the existing API. Okay. So solution overview. What do things look like at startup? Here I have a cartoon of an application. The black circles are the operators. And in front of every one of the operators, I have a FIFO queue, and it is single producer, single consumer, which means that if you have 2 threads on each side, no synchronization. That already existed in some other parts of the product. But the data structures we have initially, we have a queues table, which is going to be able to, given one of those operators, it can tell us which is the queue for that operator, and that queues table does not change, But then we also, at startup, we have a free ports list, which is a lock-free list, and that will change over time. So what we're going to look like in execution is we're going to have a bunch of threads, of course, and the threads are going to pull things off of the free ports list, and then they're going to go off and they're going to execute something, and then they're going to go back on that same queue and execute that operator. So the PE is going to maintain this thread pool dynamically, and when it pulls something off of the queue, it's not going to just execute one tuple, go back to the free port list. We're actually going to have it execute a whole bunch at a time so that it doesn't go to the free ports list as much as possible. So what does this actually look like in practice? So the finding work, oh, and by the way, so all the algorithms for this are in the paper. I made a decision not to actually show the code in the presentation because I didn't want to get bogged down in the weeds for it. Think of this as more of a something that accompanies the paper. So I'm going to go over the two main algorithms for the lock-free algorithms that go on inside the scheduler. The first thing is we need to be able to find work. So the first part of the, and this is the same, this is the algorithm that all the independent threads, so all the yellow guys on the left here, this is what all of them are going to independently do. So they pop something off of the free ports list, they inspect it, and they say, is this, so first they need to, once they pop it off the free ports list, they're going to go to the queues table to find the associated queue. Once they find that associated queue, they're going to have to ask, is this actually free? So the free ports list is a little bit of a misnomer. It's actually a potentially free queue, and I'll get into why that is in a moment. They're going to ask if it's actually free. If it is actually free, then they're going to drain the queue completely. We did experiments where we maybe only executed one, or we executed half, or executed a quarter. It is actually much better if you just drain the whole thing, because what that does is it prevents you from going back to global data as long as possible. And that is the name of the game here. Avoid going to global data as long as you possibly can. So once it drains the queue, then it will finally go back to the free ports list. On the other hand, if it's not actually free, if it's potentially free but not actually free, we're going to stick it back to the free ports list, which is what we do in the other case. So what this free ports list will kind of be is a LRU of all of the operators that are in the application. This is kind of naive. I mean, it's just a FIFO lock-free list. But in a streaming system, you actually want to be able to balance the load across everything in it as much as possible. I did a whole bunch of attempts with trying to do it different ways, and every other thing I tried to do ended up turning into basically a batching system, which we are not, in terrible throughput and terrible latency. So why do I say that these are potentially free? Why can we not just pop something off and say, I own it, and then execute it? The reason is that when I'm one of the threads doing work on behalf of an operator, I need to push stuff into the next queue for the next operator. And when I do that, it is potentially true that the queue is full, in which case I'm blocked and I can't do anything. So I'm going to, if I find a queue that's full, I'm going to try to push it into the queue. And if it succeeds, we're done. We can go back and do a normal thing. But if it's not, I'm blocked. So what I'm actually going to do is I'm going to then try to execute that operator myself. And this is why the free list is actually a potentially free list, which is and this is why I say we're mostly lock-free, which is I have a flag, which is essentially a lock, which tells me whether or not an operator port is actually free. And because we have this little lock here, it allows us to not have to go back to global data to find work to progress. The other principle here is that I'm a thread, I'm blocked on inserting work into this particular queue. This operator here that is not executing at all is the one that is blocking me. The two most important things for me to do are to push a tuple into this queue or execute it myself to clear it myself. The benefit of this is that I avoid going to global data. And I can do this without having, and I can do this with as little synchronization as possible. And this is what actually enables us to scale. Okay, so that's an overview of the scheduler. Now I'm going to give an overview of the elasticity rules. And First, before I actually talk about the rule itself, I'm going to give cartoons of what the rules are. And these are going to imply various data structures. You can read the paper to see what the actual data structures and what the actual algorithms are. So on the x-axis of this cartoon, it's the number of threads that we're at. So left is low number of threads, on the right is higher number of threads. And then the y-axis is the throughput that we see at that thread level. And then the red pointer is basically our current level that we're at. And then the blue line is the history that we've observed up to that point at those various levels. So that implies a whole bunch of vectors and remembering this and remembering that. So the first rule we have is, if I'm at a particular thread level and everything below that thread level sees a performance improvement, but I don't know what's above me, let's just go up and increase the thread level. So the next rule is, if I'm at a thread level, if everything below me indicates a performance improvement, everything above me indicates performance improvement, let's increase the thread level. A special case to make everything kick off is if I'm at thread level 1 and I don't know what's above me, increase the thread level. If I'm at a particular thread level and I do not know, I don't trust the data below me, so this is actually an important point in this, is that I might actually have data for the thread level below me, but I might not trust it anymore because I've seen evidence elsewhere that the throughput might have changed. Let's decrease the thread level and get data we actually trust. And again, if I'm at a particular thread level and I see that below this thread level there is evidence that it's just as good, let's decrease the thread level. And then finally, if none of these other conditions are met, then we're probably at the apex of our performance curve, and let's just stay where we are. Okay, so get into some of the experiments. These are synthetic experiments. What we're doing is, at the source operator, we're pumping through as many tuples as we can. And in this particular experiment, we have a 10-way data parallel split, and then we have 100 operators in each pipeline. We did this performance on both Xeon and Power systems. And this is, the Xeon system's 176 logical cores. The Power system's 184 logical cores. And what I like to do in this situation is, we have customers who care, they have maybe, their operators might do like a little bit of work. Then we have other customers that might have operators that do a huge amount of work. So it's difficult for us to pick a particular work size and say that's the representative work size. So what I like to do is I kind of like to cover the spectrum. So on the left-hand side, this graph right there, the cost is one floating point operation. Trivial. I mean, very unlikely you'll have very many operators doing that, but it gives us an idea of really what is the overhead of the system. In the middle, that is 100 floating point operations per operator, and on the far right, it's 1,000 floating point operations per operator. Okay, so now I need to explain the various options that we're looking at. So manual is the old threading model, and that is where the user placed the threads exactly where they want. And if they don't do anything, then they get one thread. Dedicated is we automatically stuck, not using all the techniques I just talked about, but we just stuck a thread in front of every operator. And this will not work well on systems if you have many more operators than the cores in your system. It'll be massively oversubscribed. The red line is the dynamic schedule I just presented along with the elasticity algorithms. And then the blue line is the dynamic schedule I just presented, but we said statically 1, 2, 4, 8, 16 threads, and of course that is a curve. So what we see is that for this particular graph, on all the systems, our dynamic scheduler actually works pretty well. But what's important to note is that the place at which, so if you look at the very, very low cost, the point at which we get the best performance is very few number of threads. And we discover that dynamically. Meanwhile, the place where we see the best performance here is, that's roughly around 100 threads, and we discover that dynamically. In the same, we have the same cost level on a completely different architecture, the place that we see roughly the same, the best performance, it's roughly at about, I think it's about 20 or so threads. We don't quite hit it all the time, but it's good enough. And that is kind of the game that I was always playing here, is I want to be good enough. because these are going to be the defaults, it's okay if we're off even by 10, 20, even 30%. We just want to have a much better default than we did before. Okay. So I want to give some intuition for what actually happens at runtime with the elasticity algorithm. So what we're looking at here are 3 completely separate runs. The x-axis is seconds into the run, so this is a time series. The left y-axis is throughput per second. Right y-axis is the active number of threads. So the throughput per second is the blue line. The actual number of threads is the red line. And what we see is that for this particular application, it's actually very stable. We can see that at the very beginning, we shoot up in terms of the number of threads. We get evidence that that is way too much, and then we do this kind of logarithmic back off to come back down, and then we settle, and then we're, for the rest of the run, we're at that number, that 6th rule, which is all the evidence tells me where we should be, and we just continue on at that point. Okay, it's not all sunshine and rainbows. So in some ways, this is a completely, you wouldn't see many applications written by users that actually had this, and that you would have a 1,000-way data parallel. That's not going to give you the right performance, but it does show that there are problems with our elasticity algorithm in that one difficulty with the current elasticity algorithms is we don't have enough history. We know what is the, what we saw at the performance of a particular thread level, but we don't keep a history of what was the time before that. So we're seeing a bunch of overcorrection going on, and this is something I would like to address in the future, but again, it's good enough. But I want to show this to say, because this is a little too perfect, so we're not always perfect. I do have a tiny bit more time, so I would like to show, because this is a product that we want users to actually use, one of the principles that I wanted to have is that, yes, we're going to do this automatically, and we want to try to do the best thing, but I also want to give controls to the users so that if we don't do the right thing, they can go in and tune it in the particular places they need to. So on the left here, we have something we added to the language for this feature, which is called threading models. So we add an threading annotation, and this user said, I do want to use the dynamic model, but I know my system. Give me 8 threads. Turn off elasticity. On the other side, we have a different application where the user had said, so in composites are the entry, they're both, the main composite for in our language is the entry point into the application, and composites are also how we group operators together. So if you stick an annotation at the main composite, it's going to apply to the entire application. So they said, yes, I want the automatic threading model, which is a little bit different dynamic. Automatic means when I wake up, I'm going to do some heuristics. I'm going to look at the application. I'm going to look at the host, and I'm going to look at the number of necessary threads, and I'm going to try to make a choice based on some heuristics, which is the best one to do. And basically, it's going to choose between dynamic and manual. Aha, but I'm an expert. I don't care about the rest of it, but I care a lot about this particular composite here, and I know this should be done with a single thread. So then I'm going to override just for this one to use manual. And then I think I am getting close to out of time. Here's the conclusions again, and open up any questions.
Really. This is great. It's a lot of deja vu. We ran into similar issues doing JDK9 reactive streaming. And I wonder if you have an acyclicity constraint in your streams, because we don't.
We don't actually. We don't either.
Well, in that case, I think there are cases where you have to conservatively generate a new thread because you do not know.
Okay. So one thing is deadlocks can happen in our system. The programmer can make deadlocks.
Oh.
So the thing is, yeah, so that's the thing is, programmers can, because it's up to the programmer, we say you have to avoid deadlocks. So they can create deadlocks. And I did have to avoid deadlocks. The difference is I had to make sure I did not introduce deadlocks that were not already existing. So we have a completely free-form streaming system. If you make deadlocks, it can happen. And the thing is that we actually have, so we have what we call a consistent region protocol, which is, because of the streaming system, we want to be able to make it so that, so users want to be able to sometimes use our applications in kind of a database-y way, which means they don't want to lose data if bad things happen. And we have this consistent region protocol that actually depends on operators blocking arbitrarily. So from my perspective, I don't know if it's truly blocked or if it's maybe just doing the consistent region protocol. So I have to do a whole bunch of work to intuit, is this thread going to come back soon? If not, then I need to remember that this particular thread is not a thread I can try to turn off. So we had to do a whole bunch of stuff because it's a real system that the customer is using, yes. So, but the punchline is, if you write deadlock systems, I can't stop you.
We do something even more evil in that there's a little evil API called manage blocker. And if you know you're going to do it, then you let us know and we do the right thing.
Yeah, like we have things that we tell you, here's how to avoid deadlock, but I can't stop you from doing it. Yeah. Oh, thank you.